So today what we intend to do is do a basic review of the concepts of stellar structure. And as you can see on your screen, these are the topics that we will be covering. But before that, let me again ask you, why do we need to study the stars? Tell me.
গঠনটা জানার জন্য বা মানে সেটাই তো স্টার জানার মানে আমাদের ইউনিভার্স সম্পর্কে অনেক তথ্য পাওয়ার জন্য আমরা
Yes, we can know a lot about the
বিফোর আগে কি ছিল হ্যাঁ এইসব আর কি
You see, we have got some fundamental interactions of nature, right? And many physics laws as well, laws of nature. Now stars provide a very interesting and a very unique type of platform where we can test these laws and as well as know more about these various interactions. Say for example dark matter. If we didn't study stars, do you think we would have got any clue regarding the dark matter? No, there are many other issues as well. So they provide a very interesting playground for us. So where we play sort of cricket using our known laws of physics, and then we find what new things we can discover. Of course, we know that it is true because a lot of new discoveries has been made, and we have also talked about it. Okay, now so basically what we will be intending to do in this is to understand the basic structure of the stars, and thereafter in the later lectures we will talk about the evolution of the stars. Now the first thing is, what do we mean by a star? Well, if you talk in very layman terms, then you can say that a star is an object which radiates energy from an internal source. It must have an internal source inside it. And the second thing is that the star is again an object which is bound by its own gravity. Now, what about planets? Well, you see, you cannot call them both planets and comets. You can't tell them that they behave like stars. The reason being that although they are bound by their own gravity, they do not radiate energy from an internal source. Okay. Again, this definition of stars, this also includes the brown dwarfs, which are not hot enough for even the nuclear fusion. That means there the central temperature of the core isn't high enough so that the hydrogen nuclei can form helium. And so again, brown, we call them such gravitationally bound objects brown dwarfs. Okay, now so with this basic discussion on stars, let us first move to this topic about what are the various assumptions that we are going to make in our study. Now, as I have repeatedly told you before, this is a very, what should I say, intricate topic with lots of detailed stuff. And as a physicist, the first thing that we are going to do is to get a gist of the most important principles by making the simplified assumptions. And then on our journey, as we move forward, we will relax those assumptions and see, and we will try to see the real picture. Okay, the real picture, what the nature shows us. Now, the first reasonable assumption that we are going to make, of course, as I have told you, this is not always the case, is that of spherical symmetry. Now, so we are going to assume that an isolated, non-rotating star which does not contain strong magnetic fields will be spherically symmetric. Now, note that all the quantities, for example, density, temperature, pressure, they depend only on the distance from the center of the star. Right? Also, hello? Yes. Now, you see, let us investigate this thing, this topic, you see. But we do know, as I've also told you before, that stars do rotate because as a result of the process of their formation, to conserve the angular momentum, as it collapses, it undergoes more and more increasing angular velocity. Remember? So now let us see what is the effect of that. Now, so we want to ask is, to what extent can we consider them to be spherical stars? And so we are going to talk about the departure from spherical symmetry. Now let us consider a mass delta m near the surface of a star having mass capital M and radius r. Now this element will be acted on by additional inward force to provide circular motion. So the centripetal force, you see, is given by this value, delta m r omega square, where omega is the angular velocity of the star. So from this estimation we can say that there will be no departure from the spherical symmetry. That means the effect of rotation will be negligible if we have this sort of relation. That means if the effect of centripetal force is less than that of gravitational force, and so this ratio is much less than 1, which gives us this criteria. Okay. Now, it is important to note that the right hand side is similar to that of TD. Now, so what is this TD? This is basically dynamical time scale. Now, how do we get this expression? You remember we talked about the dynamical time scale when we asked ourselves what will happen if the state of the hydrostatic equilibrium is violated. That means if it is violated, then how fast do changes occur to the structure of a star? And if you remember, then what we did was we found the free fall time scale. কি করে করেছিলাম ওটা? S is
একটা স্টার কোলাপস করতে কতক্ষণ সময় লাগছে?
Yes. You remember S is equal to, if you remember that basic term, S is equal to ut plus half at square. Now if u is equal to 0, then S is approximately equal to half at square or approximately at square. Now in this case, we want to know the entire time to collapse. Now if S is the acceleration, right, if S is the acceleration, S is equal to at square, A is the acceleration, S is the distance, let that distance be equal to that of radius r, and then t is the free fall time scale. Now you can use that acceleration as your acceleration due to gravity. So the free fall time scale will become root of radius divided by the acceleration due to gravity. And if you do the maths, you will get this term. where r is the radius. You do this, okay? এটা আমি অর্ডার অফ এস্টিমেট তোমাদেরকে বললাম। সো জাস্ট ওইখান থেকেই আসছে s is equal to approximately equal to at square, where এর জায়গায় we will be using the acceleration due to gravity, since we are considering the free fall, right? Remember, when we are talking about free fall, we are talking about the case where all the mass shells are accelerated inwards by gravity, and so the acceleration will be given by the acceleration due to gravity. You do this and show me later on. Now, okay, so if we do that, so this Td is the dynamical time scale, and as a result of this we get the condition for neglecting the rotation. When the rotation is not that important, then we get this condition in terms of the angular velocity of the star and the dynamical time scale. Now for our sun, this dynamical time scale is of the order of half an hour or so, and the rotation period, you see this t is of the order of 1 month, and you can find easily that we have this thing, right? T is 1 month and Td is of the order of half an hour or so. Now this thing is true, so for a majority of stars we can ignore the spherical symmetry violation. That means they are all mostly spherically symmetric. However, there are stars which do rotate very rapidly, and so there, in that case, the rotational effects has to be included. হ্যাঁ বলো।
স্যার এই জায়গাটা বুঝতে পারলাম না, আরেকবার বলুন।
দেখো এখানে কি করছি আমি, what I did right now is we used this omega square, we got this relation, then I told you that using the relation is approximately equal to at square, where a জায়গায় g যদি রেখে দাও, so you will get the t equal to root over r by g. Now g is the acceleration due to gravity, so you get t like this, the dynamical time scale. এটা যদি আমরা ইউজ করি, then this relationship, you see equation 5.16, it turns out to be like this, okay? Now this is, what is this? Omega. Omega is the angular velocity. Now you can write it in terms of the rotation period t, this thing. তাহলে এইখান থেকে more or less একটা estimate পাওয়া যেতে পারে. This relationship is similar to that of t greater than equal to, much greater than equal to Td. So if the rotation period of the star is much greater than the dynamical time scale, then we can say that the star is approximately spherically symmetric. বোঝা গেল?
হ্যাঁ স্যার।
Okay. Now what about the magnetic fields? Well, we do know that magnetic fields play a very important role in stars. Seeing the sunspots of our sun, right? Now also you see the magnetic fields are very strong because the sunspots, from there we can get estimation, and the estimation gives you, I'm not talking to you about right now, I'm just telling you that from the sunspot various measurements we can get an estimation of the solar magnetic field to be order of kilogauss, right? Now suppose the same field fills our entire sun, then let us find the magnetic energy, and you can estimate this like that, and after that we can again, similar to the previous case, we can do a ratio of the magnetic field to that of gravitational, magnetic energy to that of gravitational energy. Previously we did that case for rotational by gravitational, now magnetic by gravitational, and you see for our sun this value turns out to be 10 to the power minus 11, very small. So even magnetic fields do not disrupt our spherical symmetry condition, but for certain stars magnetic fields become very, very important, like pulsar, right, very rapidly rotating neutron stars, right. For them the magnetic fields are very strong, and we have this term is much, much larger in that case. Any questions? If not, then let me talk about the second fact, which is that of isolation. Now, you see, in our solar neighborhood, the distance between stars are very large. So, for example, our Sun's nearest stellar companion is Proxima Centauri, which is at a distance of 1.3 parsec. And so, if you do a ratio of the solar radius to this distance, you see the order, it comes out to be 10 to the power minus 8. So this means our Sun, after formation and so on, it is almost in isolation. So this means that we can ignore the gravitational field and radiation of other stars when considering the stellar structure of the Sun. Now I am talking from the perspective of the Sun, but this can be said in general. Okay, so this is one of the assumptions of stellar structure, that the stars are formed in isolation. And also this is an important, considering the distance, we can also say that almost the stars do not collide each other. Now this is not correct always, but this is an assumption and true most of the times. So this means that once the star has been formed, the initial conditions rather than the interactions with the other stars determine evolution. Now this is true for single star system. Single stars, right? Now we do know that there are also binary stars, and for those stars, in fact, this statement is absolutely incorrect. In case of a binary star, it is basically the interaction with its binary pair that will determine its evolution. I will talk more about it when I talk about Roche lobes and binaries. Okay, so now let me talk about the initial composition. Now suppose the star forms from a molecular cloud with a composition of hydrogen given by mass fraction X, helium given by mass fraction Y, and other elements, which basically the metallic composition, also known as given by Z. Of course, X plus Y plus Z equal to 1 as per the definition. Now, it is reasonable to assume that initially the composition is constant throughout the star, which means these X, Y and Z as a function of the distance from the center is a constant. Now this is not true once fusion starts, because after fusion starts, what happens? The chemical composition of the stars change, and so these various X, Y and Z, they start changing as a function of R. Note that not only as a result of the fusion, not only the composition changes, but also as a result of the heat generated due to the fusion, convection starts in. And as soon as the convection starts in, there is a mixing between the different layers of the stars, and this also changes the X, Y and Z as a function of distance from the center. Okay, fine. Now, any questions till now? Uday?
No, sir.
ठीक আছে?
ঠিক আছে, sir.
Okay,
Yes, sir.
okay. Yes, I am talking about very basics till now. Okay. Acha. Now let me talk about Newtonian gravity. Of course, we know that it is an approximation to Einstein's theory of general relativity. Now let us estimate the escape velocity. for our sun, you see, it comes out to be 620 kilometers per second. It's a very huge number. But again, compared to that of the speed of light, it's very small. So this means that the gravity in the sun is very well approximated by ordinary Newtonian formulas. However, note that this is not at all true for neutron stars. Now, I will talk to you more about it when I talk about the neutron stars, if time permits. Okay. Now, regarding the static or the dynamical, what are the implications of the violation of the hydrostatic equilibrium? That means, just I have talked about, right? If the hydrostatic equilibrium, which is the equilibrium between the gravitational collapsing force and the internal pressure of the gas particles constituting the sun, they reach an equilibrium known as the hydrostatic equilibrium. Now suppose this equilibrium is violated, then the structure changes at a time scale known as dynamical time scale. And this dynamical time scale, you can find it, as I just showed you doing the calculations, it comes out roughly of the order of half an hour or so. Now, however, we do know that the sun is not collapsing or exploding on this time scale. Why? Come on, look at us ourselves. From our age, we have been living for so long, for more than 20 years or more than 30 years or so. Now this time scale, dynamical time scale, is of the order of 20 minutes. So had something like that would have happened, the rate of the luminosity of the sun, the first indications would have been the change in the luminosity of the sun. We would have been affected a lot by that. But we are not getting such things, right? Of course, sometimes the effects of solar corona or so, they change over time, but what we are talking about here is a different aspect. You see, the time scale is of the order of half an hour. So if it gets violated, the luminosity will change drastically and we will be able to understand, but we have not observed such a thing. So this means that our sun is quite nearly static. And inside the sun, changes are quite slow due to the changing composition, which have time scales of the order of giga-year, and also the mass loss, due to the mass loss from solar winds, which even has even more longer lifetimes. Now, we do know that there are certain stars which pulsate. Right now we are not going to talk about them, but note that of course they cannot be the static stars. Okay. Now, so with this basic discussion on the assumptions of the stellar structure, the various assumptions of stellar structure, so let me move forward to discuss about the three most important equations of stellar structure. The first one is the hydrostatic equilibrium, which means that the weight of each layer is balanced by the pressure in that layer. And then I will talk about the equation for continuity of mass, which means that the total mass equals the sum of the shell masses, so this means there are no gaps in between the various shells. And the third equation is that the equation of continuity of energy, which means that the total luminosity equals the sum of the energies generated in each shell. Now the fourth equation, which is the equation for radiative or convective energy transport, we will cover in a separate lecture. Okay, so now Before I start, let me just again recap a little bit about the hydrostatic equilibrium. So, you see that we know that the energy is generated in the most hottest zone of the star, which is the central part, and then it is slowly carried outward to the cooler surfaces. Now, as you can see from the picture over here, the gravity, it acts inwardly. However, the gas pressure, it acts outwardly, and these two are balanced, and the star is stabilized by the hydrostatic equilibrium. And we can say when they are balanced, we can say that the star is stabilized. Also do know that the star is stabilized and kept under control by the nuclear reactions as well. If there had been no nuclear reactions, then the stars would have started to shrink under the effect of the gravitational force. I will show you just this in a few minutes. Now you see, so basically we have got a self-regulatory feature in the star. Let us check this in a little bit more detail. Now suppose the fusion rate due to the nuclear reactions, they increases slightly. Then what will happen? Because of the increased rate, the temperature will increase. And so the equation of state or the pressure, which depends on both temperature, density and other parameters, it will also increase. And as a result of this, the core, which is the hottest zone of the star, will expand. Now, as the core expands, the density and temperature, they will both decrease, as a result of which the fusion rate goes down. So you see, basically we have a feedback mechanism which prevents the fusion rate from skyrocketing upwards. Now, of course, there is a loophole, and this happens during the helium flash. That I will talk to you, that I think I have talked to you previously as well, and I will talk to you during the revision of the nuclear astrophysics part. Now, what would have happened if there had been no source of energy in stars? I will come to this point during the end of the lecture today. Okay, so till now, any questions? Okay, so if no questions, let me move forward. So the first thing we are going to do is that we are going to use the spherical symmetric system to describe our star. Now, let r be the distance from the center, and so the density and other parameters as well, they will depend on the function of the radius or the distance from the center. You see? And so the mass interior to this shell here is given by this expression, and the differential form of this expression is given over here. Note that there are two equivalent ways of describing the star. One as a function of the distance from the center, another as a function of this mass m. Now we have found that the second way, function of this mass m, is more convenient, because the total mass m of the star is fixed, right? The total mass of the star is fixed, while the radius r evolves with time. Okay, so a little bit change of notation. Now let us denote this mr as the mass enclosed inside a sphere of radius r and having density rho r. Then, as I have just shown you, we can write it like that, and the differential form being this equation. Now this is the first stellar equation, also known as equation of mass conservation. Now, an important application of the continuity equation is to express physical quantities not as a function of the radius r but of the enclosed mass radius, as I have just told you, and this facilitates the computation of stellar properties as a function of time. Right? Since the mass remains constant during the evolution, overall mass, whereas the radius of the star changes. Now, a radially symmetric mass distribution produces a similar Gauss law to that for the gravitational force, and it would be concentrated at the center, r is equal to 0. Therefore, the gravitational acceleration produced by this mass mr is given by this term, and if the star is in equilibrium, then this acceleration is balanced by a pressure gradient from the center of the star to its surface. Since the pressure is defined as force per area, we can write it like that. So, a pressure change along the distance dr corresponds to an increment. You see, we have written this like that in terms of mass and acceleration of the force F produced by the pressure gradient. Note that for increasing r, the gradient dp is less than 0 and the resulting force df is positive and therefore directed outwards. And in this case, the hydrostatic equilibrium requires this expression. It is important to note that if the pressure gradient and the gravity do not balance each other, then the layer at position r is accelerated and we get this relation which is known as the equation of motion. So, this is the actual relation, equation of motion, and in case there is a balance which is there, then the layer at position r is not accelerated and we get the equation of hydrostatic equilibrium. Now we can get a different form of hydrostatic equilibrium from this one by using this first relation del r del m. If we use that, then we can get a different form of this hydrostatic equilibrium, r to the power 4. And here we have left hand side we have dp dm. Okay, now let us make a rough estimate, order of magnitude estimate of the central pressure. So from this expression, you see, we can just take the central values. So dp dm, capital M at the surface minus that at the center, which is 0. Similarly, pressure at surface minus pressure at the center, and this we get approximately this value over here, you see. And so if we do that, we get this relationship. This is a very order of estimate value, right? So we get Pc of the order of 10 to the power 9 atmosphere. Okay. Next, let us find a lower limit of the central pressure. You remember we have done these things before. And so if we do that, we get this relationship, you see. And this is less than 0. Now this quantity, this one, is therefore a decreasing function of r. At the center, the second term vanishes because mass is proportional to r cube for small r, and hence psi at 0 is equal to central pressure. Note that at the surface the pressure is essentially 0. We know this from the fact that psi must decrease with r. We get this relationship. So central pressure must be greater than this value. So we get a lower limit on the central pressure. Okay, fine. Now this is a strict mathematical result, unlike the previous estimate, which is just a order of magnitude 1, and this is valued for any stars in hydrostatic equilibrium. I think you remember when we
স্যার সাইডে একটু ডিফাইন করবেন আরেকবার
side just a this term left hand side expression
আচ্ছা
here we have এই পুরো টার্মটাকে আমরা
ওইখানে
সাই বলে আর কি রিপ্রেজেন্ট করি
আচ্ছা আচ্ছা
okay now if you remember the first integral theorem that we talked about there we already used this concept a similar concept to get the various limits we use this concept during our first integral theorem's derivation that I have already talked about in a separate video. Okay, so after this let me now start a separate topic, which is now we will talk about virial theorem for stars, and let me first do prepare a background for it. Now we do know that the general form of the equation of state, right? So can anyone tell me first what is an equation of state? Well, this is very basic, right? Basically
একটা যে কোনো একটা স্টেটকে যদি আমি যে কোনো একটা জেনারেল ইকুয়েশন দিয়ে আমরা সেটাকে রিপ্রেজেন্ট করতে পারি তাহলে সেটাই সেই স্টেটটার ক্ষেত্রে ইকুয়েশন অফ স্টেট হয়ে যায়
yes,
সেই
basically it describes, you have to say it describes the microscopic properties
এক্স্যাক্টলি মাইক্রোস্কোপ প্রপার্টিজ
and generally এটাকে আমরা কিভাবে এক্সপ্রেস করি we generally express it as the relation between pressure and the different
temperature
yes different related quantities. So we write P as a function of density, temperature, composition. These are true for the stellar matter. Okay.
yes sir
Okay. Now, so you see one of the general forms of the equation of state, you can write it like this. This is a relation between pressure and energy, internal energy, U. We can write it like that. Energy density. Now, let us investigate how does this look like for the case of an ideal gas, non-relativistic case. So as you can see from the screen over here, we can write it like this, and after defining the kinetic energy per particle, we can get the value of the internal energy of ideal monoatomic gas like this, which is equal to the kinetic energy of all particles. But we do know that the kinetic energy per unit mass, right? Sorry, we do know that the internal energy per unit mass is given by this term, you see, using equation 1, and thus we get this value. তাহলে এইখানে for a non-relativistic ideal gas, this phi, this was the general form, this has a value of 3/2, and we can write this equation of state in this form as well, where U is the total internal energy, which is equal to the energy density into the multiplied by density. Now we have already showed in our notes previously that for the extreme relativistic case, the phi value of phi is equal to 3. I will talk about it in a different lecture, this derivation, again when we revise. Okay, so now we just talked about the general form of the equation of state. So let us now start with the derivation of the virial theorem for the stars. So the hydrostatic equilibrium equation written in forms of dpdm is like this. So this is equation 1. Now if we multiply this equation by 4/3 pi r cube and integrate over this mass m center to the entire mass, this r varies, right? At center r is equal to 0, and you see we are talking about dm over here. So m varies from 0 at the center to capital M at the surface. Now if we do that, remembering that the gravitational potential energy omega g or omega is equal to this, then you see the right hand side of this equation 2 is just 1 by 3 of gravitational potential energy, whereas the left hand side can be evaluated like this, where we have considered the limit at both the central and the surface values. देखो central small r is equal to 0, surface small r is equal to capital R. If we do that, remembering that pressure at R is equal to PR, then we get this relationship. Okay, now you see this very simple relationship, we can write it like this, okay, where PR is the pressure at the surface of the volume or surface of the star. Now this, the expression, if we write it in this form, is useful when the pressure from the surrounding layers is substantial. Example, when we consider only the core of a star. If we consider the star as a whole, however, the first term vanishes because, why? Because the pressure at the stellar surface is negligible and we get this form. Okay, and since dV is equal to dm by rho, we get this form, which is the general form of the Virial theorem. Okay, now this form tells us that the average pressure needed to support a star in hydrostatic equilibrium, you see, this form tells us that the average pressure needed to support a star in hydrostatic equilibrium is equal to this value, minus 1/3 R by V. Now in particular, it tells us that a star that contracts quasi-statically, which means slow enough to remain in hydrostatic equilibrium, must increase its internal pressure. Okay, since you see this EGR increases while its volume decreases. Ebare, what we will do now, we will see the effect of this Virial theorem for an ideal gas. Now we just found this relationship for an ideal gas, right? U is equal to 3 by 2 P by rho, and if we put this value over here and do the integration, then we get this value. That means internal energy is equal to minus half of gravitational energy. Right. Now, let us do a very small problem, which is starting from the general form of the Virial theorem, which I have just shown over here. We have to show that for stars of equal mass, the denser star is the hotter one. And basically what we are going to do is we are going to find the temperature, okay, and then we will be getting our result. Okay, now you see this relation, this equation.
স্যার ওই ডেরিভেশনটা কি আমরা আমাদের করতে হবে যেখানে phi এর ভ্যালুটা এক্সট্রিম রিলেটিভিস্টিক কেসের ক্ষেত্রে 3 হচ্ছে?
ওইটা you did that, right? During the internal examinations this question was there.
Exactly, হ্যাঁ স্যার,
Exactly. আর ওটা আমরা তো খুব স্ট্রেট ফরওয়ার্ডলি করেছি। কিভাবে করলাম? We use the pressure integral. Remember?
Pressure integral.
Right.
হ্যাঁ স্যার, হ্যাঁ স্যার।
Right. We use this form, this phi, we use the pressure integral theorem, and then we found for the extreme relativistic case this phi is equal to 3. এটা আমরা করেছি।
হ্যাঁ স্যার, মানে এখানে আমরা ইউজ করছি ওই p equals to 1/3 u রিলেশন থেকে আমরা ক্যালকুলেট করার চেষ্টা করছি।
হ্যাঁ, রাইট। এটা আইডিয়াল গ্যাসের জন্য। আচ্ছা, নাও ইউ সি, okay, for an ideal gas, now here we expect the gas in the stellar interiors to be completely ionized atoms, so that we will assume that our gas is monoatomic. We write it in this form. Now again the internal energy, this form we wrote down, and we get the same old result that I have just talked about before. Okay, we are getting this result. Now note that right now this internal energy, you can write it like this and evaluate to get this value, where the average temperature is defined like this. So from this relation we get this value using the Virial theorem. Okay, now from dimensional arguments আমরা ওমেগা কে সবসময় একটা some form of alpha, okay, যেটা will depend on the form of the star, mass distribution basically of the star, and of course we know that alpha's value is less than 1. You can also check it by yourself, and thus the value of T average here comes out to be this form. And if we write R in terms of the average density, then we get this very interesting result. You see, so T average depends on this mass m to the power 2 by 3 and average density. So this means for stars of the same mass, the T average will be directly proportional to the rho average to the power 1/3. So a denser star will have a higher value of the average temperature, right? This also means that if a star contracts, what will happen? Its density will increase
And the temperature will also
and the
decrease.
temperature will increase. And if it expands, its density will decrease and the temperature will also decrease. Okay. Next, I have just, for the sake of completeness, I have also given here yet another very small but interesting problem on Virial theorem. You see, let us consider a globular cluster of stars which has about 1 million stars. Now, the stars inside such a cluster of radius 10 to the power 20 centimeter have random velocities. Now we have just given you the estimate, a rough number, random velocity, order 10 to the power 6 centimeter per second. Now using the Virial theorem, if I ask you to estimate the mass of the star cluster and also the number of stars in it, considering the average mass of a star to be 10 to the power 33 gram, then how do we do? What we do is very simple. We relate the kinetic and potential energies, and you see the total kinetic energy of a star cluster is just this value, where n is the total number of stars, right, having mass small m. Each star has mass small m and v is the velocity. We also know that, and we can find we also know the value of the gravitational potential energy, and so if we do equate both of them, then from there we get this value of nm, right? So this gives us the total mass of the cluster, and from there if we put the value of small m, we get that the star has indeed about million stars in it. So this is a very basic application of the Virial theorem. Any questions? Well, if none, then let me move forward again with the Virial theorem. Okay, now we have just shown you that how you write, so you can write the general form of the equation of state in this form, where this phi has a value of 3 by 2 for a non-relativistic case and equal to 3 for a gas of relativistic particles, right? Now, if phi is constant throughout the star, then we can integrate the left hand side of which equation? You see equation 2.23, this equation. We can integrate the left hand side, this one, of this equation, and we will obtain a more general form of the Virial theorem, which is this form. It's a very fairly simple form, this one. Now let me talk about the total energy of the star. You see, the total energy is the sum of gravitational potential energy, its internal energy, and also the kinetic energy due to the bulk motion of the gas inside the star, and not the thermal motion of the gas particles. So the sum of the three terms. And note that the star is bound as long as the total energy is negative. So you see, from general form of virial theorem, we get this term. Internal energy we have gotten related to the gravitational energy. So the total energy term, we get two terms related to the gravitational energy. Fine. Now for a star in hydrostatic equilibrium, we can set this value equal to 0. Kinetic energy is equal to 0. And just I have talked about, so if we do this sum, we have got now, instead of 3, we have got 2 terms. And if we use this previous relationship, then we get this value. What does this mean? Total energy, this value, this means that as long as phi is less than 0, the star is bound. Right? And so a gas of non-relativistic stars, non-relativistic particles, if we have a star made up of them, then we can have a bound star. However, for the relativistic case, phi is equal to 3 and the total energy is equal to 0. Right? It is marginally stable, or you can say it is just at the boundary or so. Any questions?
Means that the energy for the extreme relativistic case is 0.
It is a result, right? If the energy is very high over there, then what will happen? The gas pressure will become very high and the gravity will not be able to bound it or so. This is the sort of the implication right now using non-relativistic sort of estimations, right? Of course, we do know that inside the neutron star, or again white dwarf also, inside the white dwarf the electrons are relativistic, but still it is bound.
Yes, sir.
Yes, still it is bound. How so? Then what happens? Note that not the entire star is relativistic. Again, I will talk to you about it later on. Okay? আমরা পুরোটা নিয়ে কিন্তু কথা বলছি না, পার্ট অফ ইট।
হ্যাঁ স্যার।
অন্য কেউ জিজ্ঞেস করলে কিছু জিজ্ঞেস করো। অরিন্দম, অর্পিতা। Okay, now let me talk about this term again in details. You see, so using u is equal to phi p by rho, আমি এইটাকে আবার ইন্টিগ্রেশন করলাম, আমি এটাকে এইভাবে লিখতে পারি, right? Let me just again tell you, repeat, I think, if you have not read me. You see, what we are going to do now is we are going to integrate this term and again get a form of the virial theorem. Now, what we observe is that for the non-relativistic case, phi is equal to 3 by 2, and for the relativistic case, phi is equal to 3. Okay? Then you see we have got these two forms for these different cases. This one is for PR not equal to 0 and this form for PR is equal to 0. Now let us concentrate on this form where PR is equal to 0. So what we see for the non-relativistic case, E is equal to minus of capital U, which is equal to half of omega, which means that our system is bound since U is positive, and so you see this is negative, system is bound. Now look at the extreme relativistic case. Here E is equal to 0, so this is an unbound system. Now as the cloud collapses, R decreases and then omega, which is proportional to minus 1 by R, this decreases as particles come closer. This increases the kinetic energy, and so virial theorem tells us that half of this omega is used to heat the gas, whereas the other half is lost by radiation outwards. Okay, now I am just repeating this. Probably if you have not understood or heard me before. Now, let me talk about again this stability condition using the Virial theorem. So, if the internal energy, you see, it changes solely based on the work done on it, then during an adiabatic expansion or compression, we have this relationship P into V to the power gamma is equal to constant. And from there, you see, we can get this relationship du is equal to 1 by gamma minus 1 d of PV. Next, we note that if the adiabatic index gamma is constant, which is not correct if the different levels are excited, then our integration gives us this value, and as a result the internal energy density, which is equal to capital U by V, comes out to be like this. And so the equation 4 becomes this, takes this form. Now if we use our previous equation 3, what was that equation? This equation. Okay, if we use this equation 3 along with this equation 5, then we get this form. This is the second form of Virial theorem, you can say. Now using the form that the total energy is equal to omega plus u, then considering PR is equal to 0, we get this total energy in this form. Now note that u is positive, and since E has to be negative for a bound system, then this means that this must be negative, right? And as a result, we get, since this has to be negative, we get this gamma greater than 4 by 3 as the condition for stability. Now what happens for relativistic particles? Gamma is equal to 4 by 3. And so the total energy is negative. This means that the gravitationally bound system is not possible. Whereas if gamma is less than 4 by 3, then E is greater than 0, positive, where we have an unstable system. You can check it by yourself that for a non-relativistic particles, gamma is equal to 5 by 3, and so E is equal to minus u plus omega by 2. So what were the things we observed here? The first thing is that since u is positive, here the total E is negative. This means the system is bound. The next thing we observed is that as the star radiates energy, the total energy E decreases. Then omega also decreases, but u increases. Since the star heats up, so if we define temperature by average kinetic energy, then we can have the specific heat, we can define like this. Now here you see, since delta T is positive and delta Q is negative, C is negative, and as a result we can say that the star is said to have negative heat capacity. Okay, so any questions? Okay, if none, then let me talk about, which I have talked before as well, the core collapse in a self-gravitating system. Now suppose that there was no energy generation in the core, then the pressure would be still high. So the core would be hotter than the envelope. But remember that the energy is continuously escaping. And as a result, the core temperature will decrease and it will slowly shrink since the pressure will decrease. And again we have the entire weight of the shell, outward shell as well. However, this would make it even hotter, and then we can have a more energy which will start escaping, and so we will have a sort of feedback loop, right? But remember, even if we have this loop, the result is that energy will keep on escaping, and as a result overall the core will collapse unless there is an energy source which should compensate the escaping energy. Now in the stars, nuclear reactions play this role. In case of star clusters, hard binaries play this role. Okay, now a very interesting problem. Suppose that a star of mass m is devoid of nuclear energy sources. Now, how would you determine its radius as a function of time? We have just talked about right now, right? That it will slowly decrease. Now I am asking you to give a quantitative estimation of it, considering the fact that if it maintains a constant luminosity, and assume that the star is still in a state of hydrostatic equilibrium. Now, if we do assume that the star is still in hydrostatic equilibrium, then the Virial theorem holds, and then we can write the total luminosity as the time derivative of the total energy. And we already found, did the expression. Remember, the energy is sum of three terms, and we can write it down. Now the kinetic term is equal to 0, and sum of just these two terms, and we can write this in a compact form like this. Okay. Now, consequently, what we get is this form. So from here we get this form. Now, setting t is equal to 0 and r is equal to r0 at the beginning of the contraction, if we do the integration, then we get this form of relationship for the decreasing radius as a function of time, where tau is a sort of time scale. So this is a very interesting question regarding the decrease in radius if luminosity is assumed to be constant and there is no nuclear energy source inside the star. Okay, now the third equation, which is the equation of energy production. Now this relates between the energy release and the rate of energy transport. I will talk about transport more in later on lectures. Now, let us consider yet again a spherically symmetric star in which the energy transport is radial and in which the time variations are unimportant. Then Lr is the rate of energy flow across the sphere of radius r, and again the same for r plus delta r. This is the rate for the sphere for radius r plus delta, this one, the bigger one. Okay, now since our shell is thin, so we have this sort of relationship, and also we have this as well, and as a result we can, if we define epsilon as the energy release per unit mass per unit volume, then the total energy release in this shell is written as this form. Thus the conservation of energy leads us to this form and from there we can write it like that, and for delta r tending to 0 we get this relationship, which is the equation of energy production. So we have till now 3 of the equations of stellar structure. However, we have 5 unknowns. You see, pressure, mass, luminosity, density, and this energy release. Next we will consider the energy transport in stars, but I will talk about it in later lecture, not today. Now before I conclude, let me talk about the 3 important time scales of the stellar evolution. This is the first time scale which I talked to you, remember. So the first is the dynamical time scale, which is the measure of the time scale on which a star would expand or contract if the balance between pressure gradient and gravity was suddenly disrupted, as for a free fall time scale. And so the value of this dynamical time scale comes out to be r by radius by the escape velocity, and this comes out to be approximately half an hour or so. And you can also write this in terms of the mean density. Any questions till now?
No, sir.
Yes. So, yes, this was dynamical time scale. Now, before I proceed to the next one, let me little bit talk about the thermal equilibrium. You see, if internal energy sources are present in a star due to nuclear reactions, then the energy loss from the surface can be compensated, which I just talked about. Now, in this case, the total energy is conserved, and then this holds, and therefore the Virial theorem states that both internal energy and the gravitational energy are conserved as well, which means that the star cannot contract and cool while keeping its energy constant. In this state, the star is known as thermal equilibrium, and the star is in a stationary state. In this case, the energy is radiated away from the surface at the same rate at which it is produced by the nuclear reactions in the interior. The star neither expands nor contracts, and it maintains a constant internal temperature. And we will talk about this thing when I talk about the nuclear astrophysics. Again, review it. We have already discussed it previously. Do note that main sequence stars like the Sun are in thermal equilibrium, and a star can remain in this state as long as the nuclear reactions are there to supply the necessary energy. Okay. Now, related to this thermal equilibrium is the Kelvin-Helmholtz time scale, also known as thermal time scale. So what is that? Suppose the nuclear reactions were suddenly cut off in the Sun. Then what is the time scale, or what is the time required for the Sun to radiate all its thermal energy? That time scale is known as the thermal time scale. And so this is basically the thermal energy divided by the luminosity. From there you can get this relationship, and it comes out to be 10 to the power 7 years for the Sun. Note that this time scale basically tells us how quickly a star contracts before nuclear fusion starts, or that is sets roughly the pre-main sequence lifetime. Fine. Now let me talk about the nuclear time scale, which is basically the time scale on which the star will exhaust its supply of nuclear fuel if it keeps burning at the same current rate. Now for this we have to calculate the energy release from fusing 1 gram of hydrogen to helium, and if we do that, you can find that this is this value, approximately 6 into 10 to the power 18 Hz. And so using this relationship, we can, again dividing by the luminosity L, where this Q is the fraction of the fuel available to burn in the core, approximately equal to 10%, and X is the mass fraction of the hydrogen initially present, 70% or so. If we do that, then we can get the nuclear time scale of the order of 10 to the power 9 years. And this gives a reasonable estimate of the main sequence lifetime of the Sun. Now, it is very important to note that the various time scales are related in this order. This is basically the ordering of the time scales. The lowest one is the dynamical, above it is the Kelvin thermal one, and above that the greatest one is the nuclear time scale. Now most of the stars during most of their time are in hydrostatic and thermal equilibrium with slow changes in structure and composition occurring in the long time scale as fusion occurs. However, do remember that certain important phases of the stars do happen which happen on much shorter time scales. Right, like the stellar collapse or supernova. For the case for dynamical time scale, and for thermal it is the pre-main sequence.